Alright, so this lesson is, well, we started in 7.3 part 1, introducing what the graph of three-dimensional shapes look like with two variables. And then we talked about finding critical values, right? We set up what critical values are, where they exist, and how we find them. And so this set of notes is where we're going to be practicing that. Remember, there are 3 ways to solve for critical values. Right? There's the 2 algebraic methods, which if I have to use substitution, we'll do an example with substitution. Or if it turns out they're linear, I can use a matrix, and we'll go over that. Or the 3rd method, which I added, is if my 2 partial derivatives come out where I only have 1 variable in each of my derivatives. So usually it's the derivative with respect to x only has x, derivative with respect to y only has y, which actually this first case we're going to look at. Alright, so we're going to be finding critical values of multivariable functions. Alright, so our first example is we want to find any critical value of the function f of xy. Alright, which means I need to find my first order derivative with respect to x. Set it equal to 0, and at the same time, our first order derivative with respect to y. Set it equal to 0, and solve. And I need to know, are there any x values and y value that make both of those derivatives 0 at the same time? Alright, so we're solving that system. So first step, find the first order derivative with respect to x. Well, this is a simple function. There's only one x term. So the derivative of x squared is just 2x. The y squared zeroes out. Alright, same thing's going to happen with the other derivative. The derivative with respect to y, well, the x squared zeroes out. And so the derivative of the y part is 2y. Set it equal to 0. That's the next step. And show that step. It's a key step, just like when we had one variable functions. My derivatives can equal anything. Right? Critical values are only when they equal 0. So it's important that you write down the equal to 0. Everything after this point is only true if and only if, strict, both derivatives are equal to 0 when I solve. Alright, so key step, show it. If you don't show it on your homework or you don't show it on the exams, you will lose points. So don't lose easy points for not showing that key step. Alright, now we solve. So this is that 3rd case. If you look, both of my first order derivatives only have 1 variable in it, right? The first order derivative with respect to x only has a 2x. The first order derivative with respect to y only has a 2y. And so this is the case where I don't have to use any method. I just take each equation separately and solve for the variable in each equation, which in this case is simple. Divide out the 2. And so I get x equals 0. And then do the same thing for the other derivative. Divide out the 2. And so I get y equals 0. And so when x is 0 and y is 0, both first order derivatives are 0, which means I have a critical value at that moment. Could be a max, could be a min, I don't know. That's my next set of notes. Alright, so we have a critical value at the point 0, 0. Alright, my original function has a critical value at that one and only point. Alright, the next example. Alright, so we've got our p of xy here. Alright, so again, to find the critical values, we find the first order derivatives and set them equal to 0 and solve the system. Alright, so first find the derivatives with respect to each variable. Alright, so first with respect to x, so again I go and look at this equation, and those are my only x terms, right? Everything else will zero away. It's considered constant, not changing, and so the derivative of the negative 4x squared is going to give me a negative 8x. The derivative of negative 4xy with respect to x is negative 4y, and then 1600y is going to give me a positive. I don't know why I went to the y. X terms, right? We're looking at x terms. 1920x is going to leave me with the 1920 as my constant. Alright, so there's my derivative with respect to x. Now my derivative with respect to y. So again, I only look at all the function parts with y in it. If it doesn't have a y in it, it'll zero away. Alright, so the first term with a y in it is the negative 6y squared. Its derivative then is 12y to the first. Then the negative 4xy, the derivative now with respect to y, is going to leave me with a negative 4x. And now the 1600 is my constant when I take the derivative of y. Alright, so there are my first derivatives with respect to each variable. Next step, set it equal to 0. Key step, show it. Because when I manipulate this, I can only manipulate it if I've set it equal to 0. Makes everything else I do from this point on true. If I don't set it equal to 0, it's not true. Alright, well if you look at these, this is the linear case. Alright, so I'm going to kind of write down here remember what it means to be linear. This is a linear case. Which means I can solve with a matrix, which I will re-show you in case you've forgotten from Math 120 how to solve with a matrix. Alright, I can put both of my equations in the form, so I can solve both for the standard form ax plus by equals c, meaning I can rewrite both of my derivatives where I set them equal to 0 in standard linear form. Meaning I can get an x term, a y term set equal to a constant term. Alright, and so since I tend to lose negatives are my Achilles heel, when I go rewrite these, I'm going to move the variables to the other side because they've got negatives. Now, you don't have to. You can move the constant over. Again, this is just my personal, and so I'm going to do them both at the same time. Alright, so this one simplifies to 8x plus 4y equals 1920, right, in standard form. And then the same thing over here. Oops, adding my 14x and adding my 12y to the other side. Alright, so this one simplifies to 14x plus 12y equals 1600. Alright, so there are my derivatives where I've set them equal to 0. I can only manipulate them this way because I've set them equal to 0. Alright, otherwise those equations aren't true. They're only true when I set it equal to 0, so make sure you show that. Alright, now I can use a matrix. Alright, because if you remember a matrix, it's an augmented array of numbers where I plug my system in. So it's my, again, matrix, which number of rows. I have 2 equations, so that each of my equations represent a row. So I've got 2 rows and 3 columns, because I'll have an x column, a y column, and a constant column. And then you basically write your row as each of my equations. So my first row is going to be this first equation, and I write just the numbers. So it's going to be 8 in the x spot, 4 in the y spot, 19, 20 in the constant spot. And then the second line is my second equation, so I put 14x instead of 4x here. Let me change that, guys. That should have been a 4x, right? 4x. 4x. So make sure you change that in your notes. That should have been a 4x. So that should be 4 in the x spot, 12 in the y spot, and 1600. Alright, so remember, this stands for x values, this y values equals my constant, alright, in my matrix. And then we'll row reduce, alright, which will give us our answer. So I'm going to flip to my calculator to remind you how to do this. Alright, so here's the calculator I have on my computer. It's supposed to emulate a TI-84, alright, at least it's got the button set up and where to go. Alright, so your calculator to remind you how to plug a matrix in. Alright, so if you look at this key here, x to the negative 1, and it's hard to see on mine, but above it, it has the word matrix. And so I have to hit second, that x to the negative 1. And then a menu should pop down, a menu should show up on your home screen. And across the top, it should say names, math, and edit. So the first thing we're going to do is we're going to edit, right? We want to go here and plug in my matrix. I'm going to select edit. You can edit any of your matrices. Usually I pick the first one. Alright, so matrix A, which actually has my matrix in it in terms of the negative because I was practicing earlier. Alright, the biggest thing is make sure your matrix is the right size. So up top, make sure it's got 2 rows and 3 columns. And then input your value. So here, since I did the positive when I did my example this time, oops, 8, enter, still working on 4, enter, positive 1920. Alright, so make sure your matrix is typed in there carefully. First column should be your x term, second column should be your y terms, the last column should be your constants. Quit, so second mode to quit. Go back into matrix, so second, that x to the negative 1. Second, x to the negative 1. It'll take you back to that home screen. Now we're going to do math, so go scroll over to the math key. Alright, then you're going to go off your page. You want to scroll down until you find double R, not the single R, RREF. That's what you're looking for. RREF. You select that, and up on your home screen, then it should pop up RREF. Alright, with the parentheses. And now you have to go back into matrix one more time. So hit second, that x to the negative 1. It'll take you in. And now you're going to select the name, so make sure you're on names, and then pick the name of your matrix. So my name in my matrix was A, so I'm going to select that. And then in parentheses, alright, so you should have RREF, your matrix, and then hit enter, and it'll solve it. And so it comes out the Gauss-Jordan reduced matrix, 1, 0, 208, 0, 1, 64. So I'm going to go back to my notes and plug them in my notes. Back to my notes. Alright, so I get 1, 0, 0, 1, 208, 64. And remember, that first line is my x value, and so x equals 208. That second is my y value, so y equals 64, and there's my critical point. And so this function, p of xy, has a critical value at the point x is 208, y is 64, and then in the next section we'll figure out if that critical value for this function is a max or min. Alright, so that's an example of the matrix method. Hopefully you remember the technique from Math 120. Alright, again, this is going to be the case we're looking at right now, so it's only going to be a 2 by 3. You should have the first row should be your first equation, second row should be your second equation. When you solve, you should get a single x value and a single y value. Alright, the next example. I'm actually going to erase this one so it doesn't show up in my next example. Alright, the next example is going to be the substitution case. Alright, so we did the third, we're kind of working in reverse order. Alright, I did the third method, the second method, and now this is the first method. Alright, the first method will work for all of them. Even if you want to solve using substitution instead of matrix, you can. You can always use this method. Alright, so I know this is going to be a nonlinear case because I've got a y cubed here, right, which means I'm not going to have a line anymore. Alright, so we'll have to solve this one by substitution. Alright, first though, find the first derivative, set them equal to 0, and solve. Alright, so first derivative with respect to x is 2x minus 18y. I'm going to go ahead and set it equal to 0. And then the first derivative with respect to y, 3y squared minus 18x. Go ahead and set it equal to 0. And so that square term means I cannot use a matrix because it's quadratic, not a line. Alright, so I'm going to have to solve with the substitution method. So this is the first method I talked about. So you pick one of your equations, solve for one of your variables. Sorry, that was kind of loud. Alright, and usually there's an easier case. Not always, but in this case there is. Right? This first equation here is a line. The second equation, there is a square function. Alright, so I'm going to leave the square function. It's more complex. I'm going to start with the line. And so I'm going to use this equation. And then again, I'm going to look over here. If I solved for y, I'll have to plug it in and square it. Alright, so I don't want to have to do that. But if I solve for x, I'm just going to take that expression and multiply by my 18. And so that's what I'm going to do. I'm going to solve this equation for the x term because it's the easier. Now again, if you did it the other process, solve for y, it's fine. It's just you're going to have to square that out. Again, not that big a deal, but it is just a little more complex. This is the work smarter, not harder kind of thing. Alright, so I'm going to start with my 2x minus 18y equals 0. Solve for x. So first step, move the 18y to the other side. So 2x equals 18y, divide by my 2. And so x equals 9 times y. Alright, and so that's what my x value equals. And so I'm going to go here. I'm going to replace my x with 9 times y. Because because that's what x equals. It's the substitution step. And so I get my new expression, 3y squared minus 18 times 9y still equals 0. And then simplify. 18 times 9 is 162. Right, now it's a quadratic, so you solve a quadratic. There's a bunch of methods. You can solve by factoring, quadratic formula, graph it, find its zeros graphically, all perfectly fine methods. I'm going to solve it by factoring. All right. First of all, I can pull out a 3 and a y from both terms. When I pull the 3 and the y out of the first term, I'm still left with a y. And when I pull, remember, pulling out means divide. So I take 162, divide out 3. When I divide out 3, I'm left with 54, and I pulled the y out completely, still equals 0. And now the zero factor property says I get a factor out of each one of my expressions. So y equals 0 is one of my zero factors, and 54, right? If I plug 0 in, I get 0 out. If I plug 54 in, I get 54 out, which means I have two critical values. All right, but that's only half the point. That's not the answer yet. Remember, I need a point. So I have to go back here to find my x value. So if y is 0 and I plug it into this expression, well, 9 times 0 is 0. So one of my critical values are 0, 0. And then this one, I plug my 54 into this expression, so I'm going to get 9 times 54, and that's equal to x, not y. X is equal to 9 times 54, which is 486. All right, which means my critical points, I've got 2 critical points. I've got one critical point at x is 0, y is 0, and then another critical point. Make sure you're careful. 486 is my x value. 54 is my y value. And so there's the critical points to this problem. All right, so my original function, f of x, y, has a critical point at 0, 0, and 486, 54, which those might be maximums, they might be minimums. Again, that's the next set of notes to figure out which one of those cases it is. All right, the last one from this set of notes. All right, so this one's the last case. All right, so again, I've got a cube term, so I know I'm not going to be able to use a matrix. So I find my first order derivatives and set them equal to 0 and solve. All right, so first order derivative with respect to x. So look at my expression. Those are the only parts that have x's in it, right? Everything else will 0 out. And so negative x cubed, when I take its derivative, it's negative 3x squared. 240x squared comes out 480x, and 5100x comes out 5100. And I'm going to go ahead and set it equal to 0 so I don't forget. All right, then my first derivative with respect to y. Right, those are the only y values. Everything else will 0 out because it's constant. And so the derivative with respect to y is going to give me a negative 4. Y plus 176, and again I'm going to set it equal to 0 so I don't forget. Alright, so if you look at these, this is just like the first case, it's just a more complex example of the first case. The first case was each of my derivatives only have one variable, right? If you look at the first derivative with respect to x, there's only x values. It's a quadratics with x values, but it is only x values. If you look at the first derivative with respect to y, it's a function with just y values and a constant. And so there's no x values. And so I don't have to substitute or do any of that stuff. I just treat them individually. I'm going to solve here for x, or sorry, for y, and I'm going to solve here for x. All right, I'm going to start with the easier one. Right, this negative 4y plus 176 equals 0 is the easier one because it only has one y term. Move the 176 to the other side, so negative 4 times y equals negative 176, and then divide by my negative 4. And so when I plug 44 in, my derivative with respect to y is 0. Right, now I do the same thing over here. Now this one's more complex. It's a quadratic set equal to 0. So there are more than one way to solve this. You can solve this by using the quadratic formula, and that's fine if you solve it that way. You can solve it, graph it, find its zeros, find to solve it that way. If you have a program that plugs in and solves quadratics, use the program. I'm going to solve it by factoring. I do try to create ones that factor. and this one is factorable. First of all, I can pull out a -3. I can factor out a -3. It means I'm dividing it out. So when I divide 3 out of the first term, I'm left with x squared. When I take 480 divide by 3, I'm left with 160x, and 5100 divided by 3 is 170. -170, right? I'm dividing by -3. Alright, this does factor. First of all, the x squared splits into x times x, and then I'm going to use the guess check method. Alright, so I need to find factors that multiply to -17. Sorry, that should be 1700. 5100 divided by -3 is 1700. Make sure you put another 0 there. Alright, so I need to find stuff to multiplies to -1700. When I add them, it adds to our -160. Well, my guess is, well, what if I have -170 and multiply by +10? 10 times -70 equals -1700, and if I take -70 and add it to 10, I get -160. And so that is what it factors into. Like I said, you could solve it using one of the other methods, and that's fine if you do. Alright, so I get each of those will give me out a factor 0, so I get 170 for the first one and -10 for the second one. So this means I have two critical values. When y is 44 and x is 170, both of my derivatives are 0, and so I've got critical values. When x is 170 and y is 44, both derivatives are 0. And when x is -10 and y is 44, both derivatives are 0. Alright, and so I've got two critical values because I got two x terms. Now y is always 44 in both critical values, but I have two critical values because I got two x values out here. Alright, so that means this function has a critical value at 170.44 and -10.44, which may or may not be max and mins. Alright, those would be the next set of notes, determining if they're max and mins. Alright, that is where we'll pick this up next time, so we'll stop there.